Hi, I'm Mark, and I'm going to walk you through a gravitational problem that could also be an electric force problem as well, or electric field. Um, I'm not the greatest artist, so you're going to have to bear with me. I'm attempting to complete a drawing of a thin ring of mass small m and of radius capital R. Over here is another object like a sphere, let's say. It's at position x naught on the x-axis. The ring is centered on the origin there. And it has mass of capital M. Okay. So the question is, what's the gravitational force of the sphere on the ring or the ring on the sphere? So let's look at it from the sphere's perspective. No particular reason, just maybe it's a little easier to draw for me with my meager skills. So I'm going to pick on a couple little pieces of the ring up here, and I'll just color those red. And we'll just say like this one at the top could be labeled dm1, and this one at the bottom could be labeled dm2. Well, there's a force of each of those little bits of mass of the ring acting on the sphere. And I'll draw vectors representing those two forces from those two little bits of the ring. You have to use your imagination because I can't draw well enough to show this, but there would be a great number, very, very great number, since these are infinitesimal bits of mass, of vectors making a cone around this sphere and pulling on it towards the ring. So the force of the sphere of the ring on the sphere is going to be different than if it were two objects like two spheres. Okay, so now let's look at a side view. Let's say this is our thin ring in side view. Oops, can't spell ring. Thin ring in side view. Remember, it's mass m, and then here's our sphere. It's mass capital M. And let's just figure out the geometry before we go about solving this. So there'll be two force vectors, we said. One something like this for dm1, and the other something like this for dm2. Well, notice that there'll be canceling vectors. The vertical vectors will cancel each other out. So there are only two horizontal vectors to consider in our later calculation. So let's draw a triangle that can represent this situation. I'll draw this for what we might call df of gravity 1. So looking at it that way, then our triangle must be capital R on that side, x naught on this side, and then the hypotenuse is the square root of r squared plus x naught squared. So here's theta, and here's our right angle. So the force vector that we're interested in would be this, and the component vector that we're interested in would be this side of the similar triangle. So we can say that f sub x must be proportional to cosine theta because it's the adjacent side of that triangle for angle theta. And that means that f sub x is proportional to x naught over square root of r squared plus x naught squared. because that's what cosine theta would be for that triangle. Okay, bear with me. I'm going to erase so I have more room on my tiny whiteboard, and then we'll come back. Okay, so I want to point out to you something. So I want to point out to you something that I didn't mention at the beginning, but I could well have mentioned that. And that is that if we look at this situation, we might say to ourselves, well, a little bit of the force of gravity must be capital G times m. That's a sphere, so we'll just treat it as a point mass, dm, a little bit of the mass of the ring over r squared. And it looks like we're going to have to integrate something. But notice one thing. Every little dm, as we go all the way around the ring, is in the exact same orientation with respect to the mass capital M. In other words, if we rotate this situation around, it's not going to look any different to us. We could look at it from any orientation, and the mass is in the same relative position. The mass of the ring, the tiny masses of the ring, are in the same relative position with compared to the mass of the sphere. So we don't really have to integrate anything, right? There's no real mass distribution with respect to position here. All dm's are in equivalent positions. So no calculus is necessary. And now we know the geometry of the situation, so what we can do is we can just write out an equation for this. If we integrate dm, that's just the total mass of the ring. Again, there's no need to integrate with respect to a position variable because they're all in the same position relative to the sphere. So we would write something like this. The force of gravity must be equal to, obviously, I'm just considering the magnitude. I didn't write any vector signs on anything. The force would be left, be negative. I'm just going to ignore that right now. Just the magnitude to get the idea across. G, capital M, the integration of dm, small m, must just be the total mass of the ring over r squared times cosine of theta. Well, we know what cosine of theta is. It's x naught over the square root of r squared plus x squared. And we know what r is. So that means that must equal G capital M little m over r squared plus x naught squared times the cosine, I'll just go ahead and put in my specific value for cosine of theta, times r squared plus x naught squared to the 1/2 power. So there you have it. G m x naught over r squared plus x naught squared to the 3/2 power. And if you teach AP Physics C for a little while, you'll note that these things to the 3/2 power show up fairly often because of the geometry of forces. Thanks for watching. This has been Mark Reef. Remember, what one fool can learn, another can.